Martin, then it's your slot. You have 10 minutes time, and your title was 8-bit breadboard computer. Have fun with Martin's talk.
Hey guys, yeah, so I wanted to just present something a little bit different. So we've looked at a lot of pretty interesting stuff that's all pretty complex and detailed. I wanted to show something a little bit different, so I'm going to try and share my screen. Let me share that one and put my slides up. So, okay, so yeah, I want to talk to you about an 8-bit breadboard computer, which is something I've been building basically in the background while I've sort of in lunch hours and things like that. So I guess the first question is, what is it? So it's a completely custom 8-bit computer built from the ground up. Basically, the idea is to build it using as sort of simple components as possible, not quite down to the transistor level, but using sort of and OR gates and at that sort of level, and then building it so that actually you can see what's going on. So it's based on a project that was done by a guy called Ben Eater on YouTube. He's got a whole load of videos about what he built. He's also released sort of circuit diagrams and designs for it. So I could kind of took that and because I didn't want to just copy what he'd built, I kind of customized it and extended it. So it's slightly different to his. It has some additional stuff that his doesn't have, and it's absolutely definitely a work in progress. And it's kind of like a 6502 8-bit microprocessor, but simpler. Actually, much simpler, really. So the 6502, historic back in 1975, they brought this out. It looks fairly complex, but it was simple enough that they could actually draw the thing on paper. So they originally did a lot of the it's got a circuit diagram and the sort of transistor level diagrams on paper. And it's got an 8-bit data bus, 16-bit address bus, and 16-bit program counter, 8-bit accumulator, X and Y registers. And in the original versions, I think it's got 56 instructions with 8 addressing modes. So it's it's fairly fairly constrained, but you can do a lot with it. Obviously, mine's simpler than that. So it's got an 8-bit data bus, an 8-bit program counter, 8-bit A and B registers, so less registers, only got 9 instructions and 4 addressing modes. But the reality is those 9 instructions basically give you the majority of what you need. A lot of the instructions on 6502 are sort of more complex operations, or they're sort of like combination instructions where you're doing multiple things at once. Whereas actually you can, with these simple instructions, basically you can move things around. You can move things to and from memory, move them into the different registers, and you can kind of do maths and all those kind of sort of basic things. It is very, very slow because it's a breadboard computer. On my version, it can run to about 400 hertz. But that's really only limited by the counter that's on there. You could probably go higher than that. I think Ben Eater's done some testing of the speed you can go, and you can go up to the sort of megahertz frequencies on breadboards, but you start to get problems with sort of effectively trace length issues that you don't have in a real microprocessor, because you're using wires and you've got capacitances of wires near each other and wires actually plugged into things. So this is the instruction set. It's pretty simple. I have a special addressing mode which you don't have on a 6502 or anything like that, which I've used to kind of shortcut and simplify things, which is effectively the implied addressing mode for some things which don't normally have it. So normal things like sort of transfer operations, like transferring accumulator to the output, would be implied addressing because it doesn't actually have any data. You're just saying move something from one register to another. But normally you don't have that for things like jump instructions and load instructions, because normally you're saying, jump to a position. The first byte is the jump command. The second byte is the place you want to jump to. But to make it so that, for a lot of my simple test programs, actually, I haven't got many lines of code, or I just want to jump like back to the beginning. You can cheat a bit and say, actually, if we just split the opcode in half and use the bottom 4 bits as the address, then for certain opcodes, you can either have a 1-byte opcode where the opcode and the data is in the single byte, or you can have a 2-byte opcode or a 3-byte opcode to do sort of more complex addressing, where you want to say actually opcode plus address or opcode plus 16-bit address and things like that. So I guess the next question after what it is why does it exist? So the simple reason is it's one of those things. It's fun, and it also kind of helps understand actually deep down how do processors really work. Because a lot of what we do, being software developers, we're working very, very high level nowadays. You don't really ever get into even machine code. But when you get down to that machine code level, you kind of have to understand how the process of function and what it's actually doing. To understand actually how do you do a complex operation like multiplication or things like that. You've got to understand, moving things between registers and things like that. So it's kind of, personal interest. It was also, I was finding that particularly in work hours, I was suffering, that problem a lot of people get is just, I'm in front of the screen, I eat my lunch in front of the screen, I basically work all the time. So it was a way of kind of pushing myself to actually do something interesting that isn't just, forcing myself to go out for a walk or something like that, but actually get away from the screen and build something. And obviously, who doesn't love blinking lights? Because there's a lot of flashing lights on this thing. So then, a super simple program. This is an example of the program I'm going to show you in a second. It's just, a few lines. So we're going to load 0 into the accumulator. We're going to add 0 to it just to reset the B register. We're going to transfer that to the output register to clear the output. And then we're going to add 2, transfer that to the output, and then jump back and basically loop around this addition. So we can do, the 2 times table addition. And then hopefully I'll be able to show you actually changing that code and doing something. You can see here on the left, these are the actual opcodes it's doing. So this is something on this computer you can do effectively the loop with effectively 3 bytes. On a 6502, you'd need more than that because you can't do the sort of implied addition kind of operations. So the bit you all actually care about is the demo. So I'm going to skip out of here and I'm going to bring up this. So it's a bit of a dodgy setup because the only way I can show it is using an iPad sort of dangling above the thing, but this is my breadboard computer. It's off at the moment, so I'm going to turn it on, and then you get the wonder of the blinking lights. So I'm just going to put it into run mode. So the counter at the top up here basically has a run and stop mode. So if I flick it into run mode, you can see it actually doing something. The beauty of it down here is you've got all of the basically the control lines, so you can see exactly what it's doing. At any point. We've got the data bus, so you can see what's on the bus at every time. It only has a single bus, so it's transferring stuff. All transfers happen across that single bus, whereas like a 6502 or more complex processor, you've got multiple buses to do that. We've got the instruction it's actually running and all this decode logic down here. This is just basically a set of EEPROMs that's doing decode, and it's doing basically random control logic decode like a 6502 does, where you put a load of inputs into it and it basically just converts that into a set of control lines. I can speed the thing up if I spin this handle. So now you can see that's running about 400 hertz, about as fast as it can go. You can't really see what it's doing anymore, but we can also run it right down to really, really slow. So if we run it really, really slow, you can actually see what it's doing down here with the sub instructions, which is a basically sub cycles. So actually to process a single instruction takes multiple cycles. So effectively you're doing things like loading the instruction into the instruction register, decoding it, and then doing something like moving stuff around. And some stuff happens on the positive clock cycle, some stuff happens on the negative. So you can see up here we've got the clock indicator. So you'll see some stuff happens when the light comes on, some happens when it goes off. And then just to prove it's a real thing and actually programmable, I'm going to pause it for a second, switch into edit mode. So then I've got in edit mode, I've got some dip switches to set the address. So this is proper old school, early programmable computers with switches on the front. I can then also switch into write mode. I've got a separate set of dip switches up here, so I can actually program. Now this command here is the add to. I'm going to do something simple and say, actually, let's add 3. And I'm going to write that, switch back into read mode. You can see it's now showing add 3 command there, switch back to run, and continue the processor on. In theory, the next time it runs the instruction, we should get up to 55 on the output. I might just speed that up a little bit. There we go, and it jumps up to 55. So now it's adding 3s. It is still a work in progress. It obviously can't run anything useful like Doom or anything like that, and I don't think it ever will be able to run anything but truly useful. But it is just, one of those fun projects. You can see here that the page register doesn't exist, so I can only address basically an 8-bit address at the moment, but that's going to be one of the next things to do. The flags register down the bottom does actually support, so it will register the point at which we overflow. So if we hit, when we hit 25, go over 255, we'll see that this, the C flag comes on. So that indicates it's overflown. So that would allow you to do things like a branch branch when you've overflown, or you can also do branch on 0, but I haven't implemented the code to detect if it's a 0, because that's a whole load of logic required. So I will just switch back to my deck. So obviously this is what an operation looks like. You can see basically cycle, this is adding 2. So in cycle 0, we put the counter out, memory register in. Cycle 1, we're basically taking the RAM value out, putting it into the instruction register, incrementing the counter. Instruction 2, we take the instruction register out again, put it into the B register. Cycle 3, we take the output of the sum and we put that into the A register. And then on cycle 4, we basically reset. And that's a transient cycle because it's instantaneous. So actually, it's a 3-cycle operation. It's just the 4th cycle becomes cycle 0 of the next operation. There are some references here. So obviously my website, which basically has nothing on it, will eventually have some stuff around this on there. I would definitely recommend going to eta.net to look at what Ben Eater's done, because he's done a huge amount of interesting stuff around this. And yeah, that's basically it. So I'm happy to answer questions and stuff in the chat and things offline, or obviously just, yeah, catch up with me on LinkedIn or Facebook or whatever.